The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, good afternoon. My name is Anna Zylik and I am with ICF. We are the vendor working on behalf of Energize Connecticut to bring these Passive House trainings to all of you. So thanks for joining us today. We will be recording this training and we will make this available afterwards. These trainings are at no cost, thanks to the sponsors of Energize Connecticut, and we are also in partnership with Connecticut Passive House. Just a quick reminder that the Energize Connecticut program is offering a 50% cost reimbursement for professionals pursuing either FIAS or FIA accreditation trainings. So this includes the cost of the trainings and the exam, and once you become certified, we'll work with you to process the 50% cost reimbursement. And if you have any questions, don't hesitate to reach out. With that, I will pass it over to Keegan, who's also with ICF, to talk about the building incentives.
Thanks, Anna. Yeah, and Scott, if you want to jump to the next slide. And yeah, thanks again, everyone who's joined us today. We're really looking forward to this series and very excited to be able to bring this to you all today. So in addition to this training initiative and the professional accreditation reimbursements that Anna mentioned, Energize Connecticut and the sponsors of are also proud to offer incentives for residential new construction multifamily projects with units of 5 or more that pursue Passive House certification. So for builders, developers, architects working on these types of residential new construction projects, interested in pursuing potential Passive House certification, there are incentives available to you to do so. I think there's one more, Scott, if you want to jump ahead. So there's pre-construction incentives that include feasibility studies and energy modeling, and post-construction incentives for actual certification through either PHI or FIAS. So if you're interested in learning more, please let us know after the webinar, or check out the Energize CT website for more information. And with that, I will turn it over to our presenter today. Scott, I'll let you introduce yourself and take it away.
Thanks, guys. Thanks, both. Hi, everybody. My name is Scott Pusey. I'm a principal sustainability consultant here at Stephen Winter Associates. We work on a variety of projects in the industry. I specifically work mostly on multifamily projects pursuing, some other above code program, Energy Star, Passive House, Enterprise Green Communities, Lead for Homes, all of those things. I work on those projects, daily. And as a firm, Stephen Winter Associates, as a firm, we've been around since 1972. We're celebrating our 50th anniversary this year, and our offices are located in those locales. But what we wanted to talk to you all today about is insulation. And not just any kind of insulation, but really good insulation in thermal bridge-free construction. So these are the learning objectives that we're going to cover today. And we're going to summarize, identify, describe, and recognize the importance of good continuous insulation, and more broadly, just good insulation in general. Here's to give sort of timeline for what we hope to get through. We do have a couple of breaks scheduled in here. So we'll talk about high performance basics. We'll get into the various types of insulation products and their installation. We'll have time for questions, and we'll also have, if there are questions, please just do put them into the chat. Anna is going to be helping me out with, interrupting me when there is a good question or something that you all want to know more about. So please do put that in right away, and try to get to it. You don't have to wait until we have a question slide. So at 2:50, we'll try to take a 5-minute break, and at 4 o'clock, we'll we should be wrapping up a little before 4, again, with more time for questions and whatnot. What we do have going on today is some opportunities for you all to join in the conversation via the use of polls. And so we use Poll Everywhere, pollev.com/SWA335. So if you can text the response to this poll question to that number, and then once you join, you can indicate what your profession is, trying to get an idea of who all is here and what you all are working on. So please go ahead. It should be active now. And if anybody's having any problems with it, please put it into the chat and we can try to troubleshoot that a little bit. Great, so I see 100% consultant so far. Thank you for responding. Great, so the architects are currently winning the participation medal. Great, so I see 47% architects. Well, you can all see the results right there. Thank you for responding. We do have another one. What's one thing that you wanted to hope to learn about today? So in using this, just use an underscore to sort of like link your response. It doesn't have to be long, you know, a few words to get at why you decided to join the webinar today. What is your will behind spending 2 hours with me talking about, and quite frankly, geeking out a little bit on insulation. But what are some things that you are hoping to learn about today? This one takes a little longer to type in. And if there aren't any responses, we can just move on, and I'll just hit the highlights. Well done. So I'm seeing some items about cost impact, developer incentives, etc. And please reach out to Energize Connecticut for the incentive piece. Keegan did a little bit of summary about that, but there's more information online available. So keeping walls dry, good interior, generally good interior management, I think is what I'm reading here. Methods and science, the methods, nerdy insulation stories, love it. Okay, let's get to it. Thank you for your responses. So why are we doing this training? Pushing for building electrification. There is a passive house pathway. There's incentives available. These are the benefits that we usually talk about when talking about good insulation, continuous insulation, that sort of thing. Lower the energy and operational savings, consistent and comfortable room temperatures. The comfortable part is a big deal. We get a lot of benefit in terms of comfort when the insulation is done well and it's done continuously. The next slide talks a little bit about the other workshops that are in this training. We're going to talk about continuous insulation. I am leading the workshop number 2 as well, air sealing and insulation for homes. We'll talk more about air sealing, which is really gets to the fun piece, if you ask me, and then high performance ventilation systems. All 3 of these work hand in hand and go together towards a high performance building. So let's talk about some of the basics of high performance building as we see it, as I see it. Building durability goes a long way when we build a high performance building. There's a lot of benefits. And when we talk about building durability, sort of, specifically a more robust enclosure that does a better job of keeping the outside out and the inside in. Along with that, though, I think about durability also with indoor air quality. You have a durable structure that's going to last and, be resistant to mold, mildew, rot, condensation, that sort of thing. You also get really good indoor air quality. There is an energy reduction and dollar cost reduction when we implement these measures. We're just using less heating and cooling to maintain the interior space. Great thermal comfort, and of course carbon emissions come along for the ride as well. In a lot of the areas that we are working, New York City, for example, Boston, DC, these carbon emission reductions are becoming more and more of a hot topic and more driven by the local municipalities. So passive house we see it as a pathway to high performance. These are some of the items that go along with a passive house build. Minimizing the thermal bridging, airtight construction, good insulation, all of these things are part of the enclosure, right? Part of the control layers of the building, the structure, the home that is being built. And it's not just good insulation, it's that the insulation is continuous and contiguous. It wraps the entire structure and creates a thermal bridge-free construction. There's good solar control by the use of shading. We see kind of on the larger the building, the larger the build, somewhat the less impactful some of the shading items can be. On a smaller passive building, that solar control can really be a major driver of decisions of the design. Airtightness is important for all types of buildings, especially passive house. This is sort of what passive house probably in my mind is known for. The airtightness followed closely by thermal bridge-free construction. And then balanced mechanical ventilation. So this is an ERV or HRV if it were passive house. And we'd be looking for a minimum of 75% efficiency on that recovery for the balanced mechanical ventilation, but quite frequently that efficiency needs to be even higher for a lot of the projects to pass the thresholds that are incorporated with the energy model. So this is not meant to be sort of all about passive house. It's sort of more about the building blocks and the basics that go into passive house. And I'll just back up and say the reason we talk about a pathway to high performance in terms of passive house, it's sort of, lays out a lot of guardrails that go into a well done and, quality built high performance home. You can do high performance without following passive house, but passive house really does have those sort of guardrails around, what your assembly, those minimum assemblies might look like. Certainly imposes the ventilation recovery efficiency. Those sorts of things are the kinds of guardrails that I'm talking about. So continuous insulation. We're getting right into the nerdy details, and there'll be lots more of these to come. So continuous insulation is meant to say that, insulation is touching insulation in all parts of the enclosure. So it looks like we've got a below grade wall here. We've got some slab underneath it. Of course, in the photo, this is a basement showing rather large pieces of styrofoam sort of overlapping each other and creating a really robust insulation layer in this basement. You can see here the window jamb, the brick detail. This insulation is covering all parts of the structure, right? There's a lot of rigid insulation around this. This happens to be an ICF detail. So not just that it's good insulation, but that it is completely wrapping the enclosure. Airtightness, right? Airtightness is one of the hallmarks of Passive House. I'm a consultant. I do blower door testing a lot, and so this is our preferred method to test is with the Energy Conservatory blower door rig that you see here, and you know, it either pressurizes or depressurizes the space that you are testing, thereby being able to know how much air is leaking through all the gaps, cracks, and holes in the enclosure. Balanced ventilation. So using an ERV or HRV, I had mentioned the 75% efficiency metric there. That's a Passive House guardrail. The ductwork needs to be highly insulated and air sealed. And in passive construction and Passive House construction, we're looking for that ventilator to run 24/7, continuously supplying fresh air and exhausting stale air from the structure at the same time, i.e. Balanced. So that, in a nutshell, is you know, the basics of high performance. And just wanted to pause here to see if there were any questions about anything that I've said. If not, I'm just going to move right along and talk about some of the options in terms of insulation. And so sort of backing up to the enclosure at a higher level, right? Insulation, the thermal control layer, the thermal insulation, as you see in the slide here, is one aspect of the building enclosure. It slows the transfer of thermal energy, heat, through that enclosure. Usually in a high performance building, in a good building, the air barrier and the thermal insulation work together. They're usually together in the same kind of assembly. So the air barrier is slowing the movement of air through an assembly, right? There are other pieces of the enclosure. We talk about the water resistive barrier. So this is the part of the assembly that protects the enclosure from water penetration. So, you know, this could even be, I guess you could even say this could be flashing. You know, that's going to keep water out of your enclosure. But it's not the same thing as the air barrier, and it's not necessarily the same thing as the vapor retarder either. If you think about flashing, you know, that's a good example that I like to use to sort of say you can have good flashing that is keeping the water out, but it's not an air barrier, right? Water runs down. Water is affected by gravity generally, unless it's, you know, wind blown rain. That's a little different, but in this example, you know, the air barrier is going to keep the air out, right? Air is not affected by gravity. It is definitely wind driven and wind blown, but you could have a really good water resistant barrier that is not keeping air out, especially as you think about flashing and sort of shingling the flashing down the enclosure. The drainage plane sort of works hand in hand with the water resistive barrier. We're talking about a drainage plane here in terms of a sort of predictable path for water to shed. Drainage plane can be created by a rain screen, for example, or if you've got brick on the outside, you know, there's always a gap between your air barrier, your water resistive barrier, and that drainage plane, right? So it's a pathway for water to come off the building. And then the vapor retarder we hold separate from the others to point out that the reason for a vapor retarder is to slow the rate of vapor diffusion across that enclosure. They're very often interchanged. The vapor retarder and the air barrier layer are very often sort of interchanged on a lot of the plans that I see come across my desk. But it is important from my perspective to note that they are different things. They are different control layers. They have different properties and different jobs. Although there are a lot of air barriers that, you know, can be vapor retarders, there's a lot of vapor retarders that can be air barriers. And that's where the nuance and the trickiness sort of gets fun. So in terms of the thermal boundary, you know, what is it? It's where the insulation is on this building enclosure. There's all different kinds of types of insulation. There's different amounts and thicknesses and areas of this insulation. There's also different qualities of install. So is it good, okay, or not so great? Good, fair, poor, however you want to call it. The insulation, is it protected from wind washing? Try to talk about that a little bit later. And is the insulation protected from moisture? Does it need to be protected from moisture? Not all insulation does, but the fluffy stuff definitely does need to be protected. So we talked about, or I talked about, two boundaries working together to manage energy, moisture, and increase durability. So those two boundaries are the air barrier and the thermal boundary. So when you integrate those together, that's when we're really getting to be in a very good place for a high performance building. They work together to control energy, to control moisture, and to control comfort. They have to function properly and have a continuous, or, you know, no gaps, no holes, no joints. They want to be aligned together, the thermal and air barrier. And we'll talk more about that as we go. Here is a nice graphic from Owens Corning. And so I wanted to pause here a little bit and just sort of take a look at some of the items that we went over, like, you know, generally on the previous slides. So there's a lot of pink insulation shown in this graphic. It is an Owens Corning graphic, so that's why. Down here at the bottom, you know, at the foundation, a lot of XPS insulation. This is usually an R5 insulation, and we've got it shown right up against the foundation wall, which is acting as the air barrier. So you've got the thermal control layer on the outside of that air barrier layer. And you can see as it moves up to the above grade walls, that exterior insulation is shown overlapping now the wood frame stud wall. Goes right on up to the second floor and is going to get integrated somehow, some way into what is shown here as a fluffy attic. It's a vented attic. There's insulation on the floor of the vented attic. And, you know, making these transitions from the foundation wall to the above grade wall, from the foundation wall even to the slab to the basement below, like, these transition points are where it gets interesting. It can be tricky. It's where a lot of the architects on the call, this is where a nice straightforward design that accomplishes everything that we're looking for in this thermal bridge free construction, you know, having it be buildable and constructible, easily constructible in the field, is going to result in yield in the best performance for the building in real life, in the actual world. And we've got more information about what that might look like, some ideas on how to make those transitions. And the other one to talk about, this room over top of the garage is a great spot for, you know, to have an opportunity where it's not quite so comfortable, perhaps, but done well, it can be very comfortable. So attic knee walls need to be treated pretty much like, you know, above grade walls, in my opinion, to have a very nice thermal bridge-free construction. And so there's a lot of transitions here in a very small space. So getting all of those transitions to work and still maintain that thermal bridge-free construction is can be difficult, but it can be done. It's possible. So, insulation materials, the basics of insulation, the basics of thermal resistance. R value is a measurement of the material's resistance to conductive heat transfer. So the higher the R value, the better the insulator. Shown here are some fiberglass bats. And so the formula for R value, I guess if you want to call it that, hours, square feet, and then the temperature at which the interior temperature and the outside temperature, that sort of delta T across the enclosure, is all taken into account when determining R value. BTU is a British thermal unit, and it is the sort of unit of measure that we talk about heat, talk about energy in the form of heat. Here's some common insulation R values. And so not all insulation is created equal in terms of its R value. Different kinds of insulation have different physical properties. This is one physical property, which is the R value shown over here. And you can also see that even for a given kind of insulation, different manufacturers and different manufacturing processes are going to result in a different R value. So within fiberglass, you could have high density fiberglass, sort of regular density fiberglass, blown fiberglass, batt insulation fiberglass, right? So there is an R value, and these are expressed in R value per inch. So if you have fiberglass bats at 2 inches and each one was R4, it would be R8 total. You can add these R values together to arrive at the overall R value of the given assembly. We've got even open cell spray foam, closed cell spray foam, and then some of the sheet goods are listed below. That extruded polystyrene, typically referred to as XPS, or polyisocyanated is another type of rigid insulation. We see a lot of this on roof assemblies, right? But the thing to note here is there's a range, and you know, they're not all the same. You need to look at those specs and really understand completely what the R value per inch is, and then look at your assembly to see what the overall R value would be once you start, you know, piling these up next to each other. So the first one to talk about is fiberglass bats. These bats, we've now got a more specific R value range, can go from, well, R19 to R23. That's sort of for a 2x6 wall. So you can get a R19 bat to fit into a 5.5 inch nominal stud cavity wall. You could go with a high density insulation version of it and get up to R23. The note here is, you know, more often than not, it's a little difficult to get the fiberglass bat insulation to be absolutely perfect. This photo here is from one of the manufacturers. It is spot on, 100, like perfect fiberglass bat insulation, an example of that. And talk more about good, bad, and ugly fiberglass install in a second. This is the next type, blown cellulose, so shredded up newspaper. You can do a damp spray application, which is shown on the left of the screen, where a little bit of a binder agent is put into the cellulose as it's sprayed into the wall cavity. It is sprayed a little damp. Its cousin, the dense packed version of cellulose, is on the right there. And so there's a netting that's put over top of those studs, and then the cellulose, is sort of packed into the openings. All of those red tape marks are where they cut holes so that they could evenly pack the cellulose into the cavity of this above grade wall. The dense packed cellulose, fair amount of research out there showing that it can act as a pretty good air barrier, especially in a retrofit application. It's kind of, opening up existing walls from the inside or outside, dense packing the cellulose in there, and it has been shown to reduce air leakage a little bit. Open cell foam. So open cell spray foam, approximately are 3.5 per inch. It does vary a little bit, but that range now is sort of like diminishing a little bit, right, for open cell foam. It is much easier to sort of scrape off. So once the installer would fill the cavity, if it was any overspray or they got a little bit too much in there, you can come back and rake it flush with that framing. It doesn't set up quite as hard as its cousin, the closed cell foam that we'll talk about next. It is hydrophobic, but it can hold water. So it can get a little waterlogged if it's not allowed to dry out. It's not a silver bullet for that, but it won't hold as much water as, say, a fiberglass or a cellulose, one of those fluffy options that we just talked about. Closed cell foam.
Hey Scott, there was a question I wanted to get to before you moved on.
Yeah, please do.
Someone asked how damp spray cellulose compares to just regular dense pack in terms of the air sealing properties.
Yeah, that's a good question. The damp spray cellulose, because it's not packed densely together, as far as I know, there is no air sealing benefit. It's more akin to like a fiberglass bat in that it's very fibrous. It's not, it's not densely put in there. And the reason it's not densely put in there, it's not really rated to be able to do that. So the dense packed cellulose, even though it's getting, pushed close together, it can still maintain those R values that we listed. They're on the lower side, like, R19. But, the manufacturers have tested it. But for the main question about can it reduce air infiltration? Not that I've seen in any studies, no. But good question. I think we were on closed cell spray foam. Yeah, R6.5 per inch. It can be air and vapor impermeable. General rule of thumb that I tell my project teams, and I think it's even on Energy Star's guidance, is to say 3 inches of closed cell foam could act as an air barrier. I think I would want to double check that before being 100% sure, but 1 inch of closed cell spray foam is not going to be a air barrier per se, but once you get a few inches on there, say around 3 inches, it does start acting and having the physical properties of not only a thermal control layer, but also an air control layer, which is one of the big benefits of closed cell foam. One of the drawbacks of this and the open cell piece are those blowing agents. So a lot of the manufacturers have made big strides in reducing the global warming potential of those blowing agents. But they're certainly not, we wouldn't call them kind of like carbon neutral. the amount of chemicals and the processes that go into manufacturing it have some of those, still have some of those concerns, although a lot of progress has been made in the manufacturing process. And in terms of inspecting this and looking at it on projects, in the field, you still need to have a good sharp eye when you do QA QC. Shrinkage can happen; it can be a concern, especially when the temperatures outside are sort of right on the limit of what the manufacturer recommends for an installation temperature. Getting the mix of the chemicals correct as you install it can also contribute to shrinkage. So that would look like some of the spray foam kind of pulling away from some of that framing material. But again, following manufacturer's directions and doing a good install can greatly improve those drawbacks. Mineral wool. So mineral wool is kind of cool in that we see it and you can install it both on the outside of the enclosure and on the inside of the enclosure. So the outside usually put on with some, well, usually, yeah, it still is kind of common practice to see this metal furring on the outside of a building. That's not really what we would call continuous insulation, with all those metal furring strips penetrating the insulation layer on the outside. But the inside version of it, you can also have interior bats, right? You can put these pieces of these pieces of mineral wool in between the studs in the cavity wall, whether it's steel frame, wood frame, whatever. It is air and vapor permeable. You see a lot of it used in rain screens. The R value is higher. You can get it in a variety of different densities, semi-rigid, rigid, etc. Those densities do affect the R value of the product. So just pay attention on what you're specifying and installing, that it's going to achieve the goals that you have. But yeah, so R14 to R24, R14 in a 2x4 wall, R24 in a 2x6 wall, about R4.2 per inch in general. It varies a little bit. All right, XPS, extruded polystyrene, typically the blue board. So Dow's product is blue, Owens Corning is pink, of course. And this is pretty reliably R5 per inch. We have seen R5.4 per inch available. It is very water tolerant. So we see this a lot on below grade walls. We see it underneath concrete slabs. It's a monolithic material with no facer, as the note says here. And, generally seen a lot, see this a lot as a solution for thermal bridge-free construction because it covers, sort of the entire wall surface. And yeah, we see it a bunch. Polyisocyanurate or polyiso.
Another question for you before you move on.
Go for it.
Two questions actually about mineral wool. Is there an application in which it can be used continuously as a continuous insulation? And then also just a question around its ability to reduce noise and like sound buffering.
Yeah, I did want to mention the sound buffering. I'm actually doing a little bathroom remodel at my place and used this in the bathroom walls because I know that it is, of the fibrous insulation, one of the best at sound dampening. The density really lends itself to that, and it does a little better job, has generally better STC ratings than a fiberglass assembly. And then in terms of making it a good continuous insulation layer, it's all about the fastening system that you're going to use to get it onto the building. And so a lot of what we have seen on some of the larger, taller projects that, need to meet this fire resistant rating, in some of, it's not wood frame per se, right? Like, so you need to have a masonry or sort of steel enclosure. And so typically what we see is a, masonry CMU wall with the Z-girt, the actual metal channels that the insulation is lying in and being held in. Those are fastened to the building using some sort of thermally broken clip. I'm not sure that I have any examples in the presentation today. I can't remember. We might. There's a manufacturer called Cascadia. Cascadia Clip is one of the ones that we see quite a bit. That's going to, hold the Z-girt framing onto the wall and sort of mitigate a bit some of the thermal bridging. Having said that, you still have these pieces of metal that are interrupting your thermal insulation layer. So it's not bulletproof. There are other options to, use. We see wood furring sometimes used. Wood furring used with the sort of rigid variety of the mineral wool, and so that can the furring can sort of sit on top of the mineral wool. There's other options for sort of having arranging how you actually have these Z-girts fashioned onto the enclosure, and trying to have, instead of like these long lineal thermal bridges caused by the Z-girt, you would try to sort of do more of a crisscross pattern and get the insulation, behind all of this Z-girt. So yeah, it can get complex. Manufacturers have good suggestions on the literature that they have, and yeah, so it's a good question, and it's a fair point. Is this really continuous insulation? Probably not. The polyiso-cyanurate, we see it used mostly on roofs, flat roof assemblies, but can be used on walls as well. Here's some of that wood lap that I was just talking about, that we see sometimes used with mineral wool, the very dense versions of mineral wool. But in this low-rise wood frame, example, these pieces of lath are just sort of holding the continuous insulation onto the structure, right? So there's long screws that are being driven through the lath, through the insulation, and landing on a good solid substrate. A lot of times there's plywood sheathing behind this. So yeah, this is sort of more of a traditional kind of way to do thermal bridge free construction in your above grade wall. Moving on to EPS, expanded polystyrene. So sort of like the white flaky, think of like, old school coffee cups. Seen here, excuse me, is some of the, why am I blanking on ICF construction, insulated concrete forms. The material is very water tolerant. R4 to R4.7 is available, and we see this sometimes in high-rise construction. It works well. for both air and obviously as a thermal control layer as well. It's not bulletproof. There's still, you know, a lot of all the penetrations and everything that sort of go through this EPS. Layer can get somewhat tricky to deal with in terms of you know, getting all the waterproofing and everything correct with the windows, but that's kind of true on every build, no matter what the insulation layer. Wanted to give special note to the zip system. This one is a little unique in that we are starting to see a lot of this kind of material, and it does incorporate, or it can incorporate insulation right into the panel. So as you can see over here in the image in the right, you know, the white strip down here is the insulation layer of the zip, and so it's integrated right into the air barrier of this structural panel. And so when all of this taping and everything happens, it becomes a pretty robust air barrier, and with the insulation baked right into it, it's sort of a one-step process, as opposed to some of the other images we showed with the polyisocyanated. You know, that's more of a two-step process, right? Like, you can't use polyisocyanated as for any kind of structure. It's usually placed over top of plywood or OSB sheathing. This zip is different in that it is all one piece. One of the higher end things that we don't necessarily see all that too much on is aerogel. Aerogel has a very high R value per inch, up to R10. It's very useful in space limited applications. We honestly don't see it very often because it's very expensive. But you know, if there's no other way to sort of mitigate a thermal bridge except for the use of something like this technology, it is available. I wanted to move on and talk more about the continuity, the insulation continuity concept. So insulation is sort of like the sweater that keeps you warm. So you see the red sweater in the image here. The air sealing is kind of like the shell that keeps the wind out. So you don't want any gaps in either one of these layers, but just wearing the sweater on a windy day is not going to necessarily keep you warm, and wearing the shell on a very cold day by itself is not going to necessarily keep you warm. It has to go together. The idea here and the image shown is of a retrofitted row house, retrofitted brownstone, where you can see on either side of the image in the middle where it's, you know, very dark, indicating not a lot of heat, not a lot of energy is escaping that shell, but its neighbors have, you know, by comparison, an awful lot. And so launching into kind of like thermal bridging, we've got another example here of what this might look like in a wood frame wall. You know, it's a nice visual representation to say that when you join all of these and push all of these framing members that are interrupting the cavity insulation here, when you push them all to one side, you can see where, oh yeah, all of that thermal bridging can add up, right? 25% of the wall surface is nothing to sneeze at. A full quarter of the wall is not insulated to, you know, the level that this batt insulation is rated to, right? There's a derate. There's a derating factor of all of these framing members. When you add them all up, it can become something to deal with. Here's some typical thermal bridge locations. We talked a little bit about these in terms of the slab to wall, the roof to wall, the windows. All of these connection areas are where thermal bridges can show up. We're going to talk about them more as we go. The cooler is in there as a demonstration of something that has very few, if any, thermal bridges. How do we mitigate thermal bridges? Here are a couple of examples. In traditional wood framing or even in steel framing, you know, this is generally how a corner would be laid out in the past. So there was an opportunity to have, you know, you didn't need the structure here, so it could be left open, and you would start the next series of stud framing as you go, leaving this open, and you know there would be no insulation. So in the previous image, like, you know, that's right here at this corner where it's, you know, 53 degrees as opposed to 62 degrees when shot with the infrared camera in a corner. So ways to mitigate that, typically called a California corner, just turn your stud here the other way, rotate it, and now you can get more insulation in there. It still is a chunk of wood in the corner of the room, but we are trying to mitigate it a bit with having and giving space for the fiberglass or whatever insulation product would be put in the cavity here. Other items below are showing a thermal block, a thermal bridge between the footing and the steel posts for heavier style construction. So the thermal blocking shown in the image here is a little different. I don't think this is the same project, but the application and the concept is the same. There exists the thing called such a thing as advanced framing. So advanced framing is going to try to reduce the amount of framing that's in the wall. So the advanced framing is represented just by the brown studs and any of the hatched studs. So reducing the traditional double top plate to a single top plate, limiting the amount of framing around, especially in headers, using ladder blocking to reduce where drywall nailers are needed, you know, to fasten drywall. All of these are examples of advanced framing. And T-Stud has come up with an innovative way to sort of use wood dowels to give, to sort of reduce the amount of framing that would be between insulation. And so just these wood dowels are sort of like in the cavity where the insulation is. So wood framing, lumber, you know, this is sort of what we're talking about in terms of thermal bridging. You want to utilize continuous insulation when possible to mitigate that, right? So exterior sheathing shown here. Here's the wood stud. It's connecting the interior environment to the outside. So it is a bridge for that energy in the form of heat to transfer across your enclosure. So we've got another opportunity for some audience participation. We're wondering what might diminish the effective R value in walls. What types of things would diminish it? We've talked about a couple of the thermal bridge items here, but we're going to review age. Sure. Water, that's an interesting response. Yeah, waterlogged insulation is not going to perform as well. So yeah, MEP penetrations for sure. Air infiltration, good answer. Compression, I think that's one of the consultants on the call. Great. So I'm going to keep moving. I think I'm a little behind the time frame that I wanted to be at by this point, but wanted to talk about installation grading. There is such a thing as installation grading in terms of evaluating how good the insulation installation is, and This is coming from ResNet. This is the Residential Energy Services Network methodology for insulation grading. Grade 1 is the best, grade 3 is the worst. This is looking specifically at the amount of gaps in compression. So grade 1 has almost no gaps in any of the insulation installed in the wall cavity. Grade 2 can have up to 2% of insulation being either with a gap or compression. And then grade 3 would be considered 2 to 5%. If it's kind of worse than grade 3, you would almost consider the assembly to be like uninsulated at that point, or start to apply a more significant kind of D-rate on the assembly. These are all for purposes of energy modeling and whatnot. But for Energy Star purposes, this grade 2 is sort of the magic, excuse me, the magic number to look at. If there was continuous insulation on the outside of this cavity wall, you could still earn the Energy Star, and by having a grade 2 cavity insulation install. Let's look at some examples of good, better, best installs and things to consider. Here's some good photos of rigid insulation. You can see that all of this exterior insulation on the CMU backup wall has been installed. It's touching each other, it's neat, it's tidy. This is showing how to fix some of that when it isn't, butted up against each other at 100%. And it's construction. We're, building these walls, on site. Not everything goes to plan. And so using some spray foam insulation to fill these gaps is completely appropriate and should be done when there's a gap. Here's some examples of some bad insulation. It's just, missing, right? Like the gaps are quite large. I would consider this, looks to be like about 1/2 inch to 3/4 of an inch of a gap maybe. And the spray foam that was applied is inconsistent. It's not at the right depth, etc. Right? A lot of these large gaps can be caused by brick ties. The brick ties are penetrating through the insulation layer. This is the brick tie right here. You can see, yeah, that's the insulation. This is the brick tie, and it's coming through, and then, this is just the gap in the insulation, right? So all of these install issues we would want these to be corrected in the field with the use of spray foam. The 1-part foam comes in the cans, can be applied pretty quickly and easily. This is sort of thrown in insulation, right? Just sort of hanging out in there. And then back to our sweater analogy, this is kind of like what you would end up with, right? Like a very holey sweater. How about more batt insulation photos, or starting out some batt insulation photos? I've got a lot of these batt insulation photos that I think I'm going to want to just sort of zip through. For those of us that have been rating and doing insulation inspections for a while, this is all like pretty common. So comparing these photos to what we saw at the beginning of the section where, the fiberglass was installed really picture perfectly, which is this, these are really great photos compared to this, where it's a lot of compression. It hasn't been cut to fit. This hasn't necessarily been cut to fit all that well, but then, the installer did not cut around this electrical box, and it's resulting in a pretty poor job, right? So this insulation, not to mention the gaps that are around here, it's also now compressed. It's not going to perform at the R19 value indicated on here. It's squished into the cavity so much, you can see at the bottom here, that's a lot of framing that you can still see. And so compare that to this, you know, it's night and day. Here's an example of mineral wool insulation on the inside. It's installed really nicely. It helps that these studs are spaced, you know, 15 3/4 inches apart, you know, 16 inches on center. That's what the material comes through from the manufacturer as. And so we get a great install. Okay, so these are a lot of photos taken from Energy Star. Energy Star has a lot of good resources for good, bad, and pretty atrocious insulation. This is indicating the gap between framing. This looks like the top plate, right? Triple top plate. And so no gap, big gap. That looks to me about a ½ inch or not, if not more. And so we want to avoid those gaps or voids. Here's an example of unfaced fiberglass insulation installed. What's being shown here is how much of the insulation has been pushed into the cavity. You can see a lot of the 2x4 looks like an yeah, it looks like a 2x6 construction, as opposed to this install where, you know, you can't see any of that facing. It's at its full depth and is going to perform as rated to that, you know, whatever the R value was. Another example of compression caused by this is electrical wiring in a cavity. You know, electrical wiring is in every cavity almost. So what you want to do is split the bat around the wire. So with fiberglass, it's really easy to sort of just peel back a layer of the bat, get you know, half of the insulation or, you know, a third of the insulation behind the wire, and then have the other part of the bat flop over top of that, splitting the bat around electricals. Here's an example again of the electrical box. You need to cut around this box so that it can be, gets into the cavity without any of those gaps. Here's a really good one with compression and misalignment with the drywall that's going to sort of follow. All of this has been, it's not cut to fit. It's squished in there. It's, you know, quite frankly, pretty atrocious. This is my favorite over here. That's probably, you know, this piece of insulation is probably the same width as this, but it's stuck into a cavity that's probably half the width. And so when you see this on site, you know, trying to figure out what the core problem, like what caused all of this, is going to go a long way in sort of communicating to the installer or whoever what the fix is. There's more bat insulation in floor systems, and so there's some exceptions that Energy Star would have for how to do this correctly, but what's being shown here is this piece of fiberglass is not fully filling the cavity. Like I said, there are exceptions for floor cavities within Energy Star, but generally what you want to see for a high performance install is to have insulation fully fill the cavity that it's, you know, you're insulating, so that it touches. This is subfloor, probably subfloor above, and you know, this might be a basement or whatever, so that it's touching both the drywall that's going to go here and the subfloor above. This photo is showing, you know, there's a lot more fill here, you know, sort of fully filling it. More cantilevers and whatnot, you know, filling these cavities. This is kind of more of an air sealing item, but the point is valid to have the insulation in contact with the subfloor above and the air barrier that's going to be eventually installed below. Tubs and showers are a good spot where insulation can sometimes get missed. You got to remember to get insulation no matter what type behind a fiberglass tub surround before it goes in. Oh, good. That's our last slide, and I'm roughly kind of on time. So that was a lot about fiberglass. Are there any questions about this? We are going to do a 5-minute break right now, and if there are any questions, please let's have them.
No questions in the chat currently, Scott, so maybe we take the 5-minute break and come back, and there might be some in there. Otherwise, we can keep moving along.
Yeah, sounds good. So let's come back. We'll plan to get going again at 3:10.
Perfect.
All right. So Keegan, if there were no more questions that came in, we're going to move on to what I would consider some more of the the more interesting pieces of today's talk in terms of trying to integrate the thermal barrier and the air barrier and kind of what that looks like.
Scott, there was one question.
Yeah.
I'm going to take a moment. Yeah, so there was a question with regards to the sweater and the windbreaker analogy in terms of whether it's better to, in a logistical application with air sealing, have the windbreaker, so to speak, the air barrier on the outside versus the inside.
Yeah, that's a good question. And we kind of intentionally use the interior shell concept with the thermal layer on the outside. So the sweater on the outside, the shell on the inside as our example. And, you know, the big thing is to have those two layers be effective, you know, doing their jobs. So the thermal control layer doing a good job at mitigating how much energy is moving back and forth. The air barrier doing the same for air. But when you have the insulation sort of outboard, a lot of times it can act as a protector of that air barrier that's on the inside. And so a lot of times too, your water resistant barrier is sort of, you know, not 9 times out of 10, a lot of times is aligned with your air barrier. And so if you can sort of protect that air barrier, water barrier with the insulation a little bit, that's kind of what we've been seeing in a lot of the design, but it doesn't have to be that way. What isn't sort of really all that great is to have like 2 air barriers, you know, an interior air barrier, an exterior air barrier, and then trying to, like, you know, have one be pretty good, or, you know, have 2 be pretty good, but, you know, they're not necessarily both, or one of them is not, like, you know, spot on 100%, like this is the air barrier, right? Like that's where we see a lot of project teams that can fall into the trap of like, well, you know, I did an exterior air barrier, maybe some preliminary testing or whatever shows that didn't quite get to the target that you wanted to. And then, you know, it's easy to say, well, we're going to put drywall on the inside. That's probably going to tighten things up. And that's not the case. It doesn't happen that way, unfortunately. You know, you want to do a air barrier and do it well, have it connected to everything. And that's what this red line test sort of gets to is, you know, can you trace around your building, around your enclosure without lifting up your pen to create this red line, you know, indicating that I don't really know how I'm going to connect the roof to the wall, right? We need to think these things out in design, have products that are going to be able to make it happen, and you know, do the details that are, you know, constructible in the field. So that's a long-winded way to sort of answer a pretty simple question, I guess. But yeah, this is what we're looking for in high performance is, you know, passing this red line test. You can see, you know, on a large scale, it's pretty easy to just, you know, draw a line around here and say, well, yeah, look, I've got windows here. They're going to be on my wall. The wall's going to connect to the ceiling. Well, yeah, you know, of course, but like in detail then, you know, what does that look like? How are you going to make this connection from, you know, here's the air barrier, like, you know, the drywalled ceiling in this case, fluffy insulation in a vented attic above, and then a framed wall that is meeting it. Like, how are you making this connection? How is that going to be airtight? And then carrying it down through the windows, you know, detailing your windows. How is all of this going to happen? Sort of, you know, talking the talk is one thing, but walking the walk in the details and on site is the other. And that's kind of the main point, in my opinion, of this presentation, is to get everybody thinking about how this is going to actually be done so that we can end up with a higher performing building, i.e. one that doesn't leak air and one that has continuous insulation. So let's talk about more of that. Here's an example of some wood framed below grade to wood framed above grade walls. So this is the detail. You know, this is a slab on grade construction. Slabs right here. There's insulation shown on the outside of this foundation wall, and it meets insulation that is shown on the above grade wall. And so what you can see here in practice, they are using the Dow Blue Board. So extra points for anybody who can tell me what that R value is. It's coming down here and meeting the slab on grade construction. There's a few things that are indicated by the circle here. One is that they haven't come by and put the exterior piece of insulation on. At least it doesn't look like. It's very typical to sort of like have this gap be filled sort of after both walls have been built. So it hasn't quite been done yet. But also more importantly, you can see in terms of the air barrier, you know, the zip tape is shown here beneath the window, connecting to the wall below. There is no tape here though. So that's hasn't been put on yet, or, you know, is potentially might get missed. So that's what we're flagging here in this image. Some other areas where it can be tricky and where there can be thermal bridges. This is an above grade wall with an overhang, right? So this porch roof, you know, has been framed right up against the sheathing. This zip sheathing is the non-insulated version, right? So there's going to be insulation that's going to come along afterwards. And so the possibility exists for this framing of the porch roof to interrupt the insulation, the continuous insulation, right, in quotes, air quotes, above. And so in detail, we want to show how to do this, right? What's this going to look like? There's 4-inch XPS rigid insulation shown, and it's showing that it sort of covers the ledger board. You know, is that going to get installed on site? We want to take a look and see if that's actually going to happen. So this is an example of, you know, a challenging detail, not only to install 100% and get that continuous insulation. This detail, as shown, you know, is tricky even to install, you know, as shown. You're going to have all these framing members, you know, interrupting all of that insulation there. So, you know, would there be a better way to do that? Probably, yeah. Let's look at window framing. So there's a concept within Passive House called window frame over insulation, whereby insulation is not only in the field of the above grade wall, and it's, you know, continuously done on the outside, but that you would also encroach, that insulation would encroach over the window frame to provide extra insulation for these window frames. A lot of older frames don't have, you know, great insulation values. This is a pretty specific kind of Passive House thing, a Passive House technique. We don't see it very much on some of the larger builds that we do. It is and can become quite a thing on some of the smaller projects, some of the single family projects where the energy models are struggling to, you know, meet the very pretty tight levels that Passive House lays out. The bigger your building gets, the sort of the easier it is to meet some of those metrics. And quite frankly, we don't see very much of this window over insulation in the projects we do. In detail, however, this is what it would seem like. You know, here's the window frame itself, right? This insulation of the wall is sort of over insulating it. It's helping to you know, reduce the amount of energy that's going to transfer through this window frame, both at the head and the sill, and even a bit at the jambs. Again, we don't see this all too often, but it is a passive house concept, and wanted to bring it up. So, wood framed, air barrier versus insulation install in the sequencing. So there's an image here of the exterior insulation. You know, this gentleman is, I believe he is removing some of this insulation because kind of got ahead of ourselves. They kind of got ahead of themselves a little bit in that I don't believe there was any insulation back here, and so they needed to, you know, remove the framing that was over top of this in order to get back to, you know, this sort of like bare wall where it wasn't installed, and then, you know, get insulation in there. So it's a sequencing thing, you know, making sure that you have got all of this insulation installed before any framing goes over top of it. That framing is there to hold the siding on the house, on the building. Some other sequencing items. It's quite typical for masons to install exterior insulation, which, you know, it's an efficient use of their time as they sort of, you know, work their way up the wall. But, you know, masons, in my experience, usually are not the experts in terms of air sealing. And so what we see here is that, you know, this zip wall needs to be insulated with exterior insulation because it's not the zip R variety. The seams have been taped, and, you know, the insulation is going on top of it. But what wasn't done all that well was actually like getting the air barrier, the seams taped correctly. The zip system insists on using a roller to sort of actuate the tape to get the chemical materials that are in the tape to sort of emulsify and seal to the substrate. If you don't use a roller to put it on, it's not going to make the seal, or if it does, it's not going to be, you know, the best seal that it can be. You can see here there's we would call these fish mouths. There's areas where it's not fully adhered. The seam between these two pieces of sheeting is sort of right here where my cursor is. So this fish mouth is connecting the seam to the outside. And when this gets duplicated over a large surface area of a building, it can really add up. And that's exactly what happened on this project. This one was one of my early passive house projects that failed the blower door test by probably about 300 CFM. And it was a 3-story, 50 apartment unit building. So it was really a tough pill to swallow, to sort of, you know that a lot of these issues that we identified during the field inspection maybe not all of them were addressed as it went up the 3-story building. And it's just unfortunate that the building just barely missed the infiltration target that passive house had indicated. But the idea here is sequencing. Who is doing this install? Is all of the stuff behind, you know, before you cover up the air barrier with your thermal control layer? Is all of that buttoned up? Is it done well? And will it perform? That's the point of the slide. an example of an energy heel. So getting to the thermal bridge that can exist between the wall and the roof using a regular heel truss. You can see that this insulation in the attic is not really in line with the exterior wall. So we've got quite a good thermal bridge right here. One way to mitigate that is to use an energy heel truss where this pitch is quite a bit steeper. Sorry, not steeper. There is more room that is allowed for the insulation to work its way into the truss, into the cavity. So now you can see we're getting some insulation above the top plate of that exterior wall. So we're mitigating that thermal bridge. Other options to connect an above grade wall to a roof might include the use of spray foam. Spray foam can be used in some of these trickier places to get to. There's a lot of caveats that come along with it, however, that we'll share now. So this is me up in an attic in Connecticut, hunting around this what looks to be a really well done, spray foamed. This is the sloped portion of the roof coming down to meet. This is the drywall ceiling above, right? So there's no fluffy insulation down here because the thermal barrier is up here above my head. But there can be breaks in the insulation, as you can see on the right here. That's just a hole in the insulation, and because the insulation is trying to act as the air barrier as well as the thermal barrier. Air coming through here is being picked up as leakage, and so the spray foam is not a silver bullet. Usually done in like small, hard to reach spaces is kind of what we generally advise. So like in this example here, this says an awning detail, but this is a rim joist area. This would be a great place to spray insulation to try to get a good install in there. Some of the other considerations with this detail on the left include more sequencing issues. So at first blush, when you look at this detail, I can see, there's an air barrier that's been indicated. It's continuous, it's touching each other, right? There's some inside and outside corners, but that can be this could be done. Then you look at the insulation and the question comes up, when is that insulation going to get installed in this sort of cantilevered floor, right? And who's going to be installing it? You can see the floor joists are running front to back, or sorry, side to side, I guess, if you were sort of, looking at it as a building's perspective. But, this subfloor is going to get installed. The bottom air barrier of this is going to get installed, and, the insulation needs to go in there ahead of time. You can only put insulation in a cavity if you have access to that cavity and that, you have a cavity in the first place. So, doing the insulation from below is possible with fiberglass bat, and then the air barrier would be put on, everything would be taped up and sealed, and then more continuous insulation would be put on after that. That's a lot of steps, a lot of different trades involved in doing that work. And so it's something to think about in terms of sequencing, who's going to do it when, and ideally we would like to inspect it and get a photo of it before you close it up. More porches and balconies. Here is an example of doing some insulation behind any sort of porches or balconies that come out. This detail is showing 1-inch high density R6. So an insulation product that would be able to withstand some of the structural forces that are going to be demanded of this. So the reason for the high density piece there. But again, you can see something that is going to continue the insulation layer that it's going to get behind there, and it's going to be continuous. Window headers. Window headers are tough. Sometimes you could do an insulated header in wood frame construction. You can put some insulation, some sheet good material between the two structural members of this header, typically called an insulated header. The possibility exists to insulate underneath the sill of your window. Here's another header that's shown, but sort of like, mitigating, there's not much structure here to begin with. There's not much framing to begin with. And so getting insulation in there to sort of mitigate that thermal bridge is what we're trying to show in some of these details. Some of the more innovative approaches to doing, especially like roof to wall sequencing, is trying to use this idea of monopoly framing. I'm going to go ahead one more slide and sort of show you what we're talking about when we talk about monopoly. Rissinger Build sort of is credited with this term, this idea of monopoly framing. It's got some good YouTube videos, but the idea, the concept behind it is to build the structure, build your air barrier first. So, this is a framed wall coming to a framed roof. The sheathing here of this roof is going to be the air barrier. Okay, so this is not a vented fluffy attic scenario, but you can see here that this zip tape is one continuous piece of tape, more or less. That's just been done just like a corner would be done, right? Pretty easy. It's done on the rake, it's done along the eave, and going back to the other slide. What you can see here is more of a flat roof application. This was the original detail that we reviewed for this passive building, and you can see that there was some fascia board. Give the structure some dimension. It's very typical to have a roof overhang. Roof overhangs are great. Keep sun and rain off of your walls. But what isn't shown here is how the air barrier of the roof is going to connect to the air barrier of the wall. And so the updated detail shows a more sort of monopoly framing approach, in that this overhang is now able to be added after the fact, right? So frame up the wall, put the roof on top of it, and then use liquid applied air seal between the roof zip sheathing and wall zip sheathing, and extend the top plate to the underside of the sheathing, right? So structure, all this is holding up the roof as you would want it to happen. And then this overhang, this eave, is added after the fact. It's added after the fact with an outrigger kind of construction. The screws are fastened in here. There's plenty of structure behind it. But this seemingly like pretty innocuous detail is sort of like what we're getting at with some of these newer types of construction. And it's not, this is not going to add a tremendous amount of cost, but it is going to really result in a much tighter construction, because you know, this is just so much easier to implement in the field and end up with a continuous air barrier. So I'm interested if anybody has any questions or comments about this. Here's some more examples of sort of this monopoly framing idea. So this is a pitched roof. Air barrier is going to be sort of at the ceiling, the floor of the attic level, right? And so there's some questions about, like, you know, how would you get this tied together and also have, you know, your roof framing or your trusses or whatever integrate into that? Because, you know, this roof truss is going to interrupt any kind of air sealing every, you know, 24, 16, 19 inches as you go down the face of the wall. Over here, the updated monopoly version of this, you know, this outrigger, this eave is put on after the fact, and the structure has been put in place in order to do that, so that, you know, you can have all of this stuff meet together, make your air seal in one continuous valve swoop, and, you know, not have to dance around all of this framing as it goes across the wall. I hope I'm explaining this, that you guys are sort of understanding what we're after. Parapet walls are also an area where it's tough to get continuous insulation. Again, this looks like a pretty standard parapet wall design, right? The question, you know, closed cell spray foam insulation has been specified here. And our question to the design team is, or to the construction team is, hey, you guys see this? Who is going to be installing this, and when will they be installing it? Because, you know, typically this parapet wall is going to get framed up, sheathed, and waterproofed like within days of each other, if not hours. And so coordinating all of this, making sure that this closed cell spray foam actually gets installed is a big deal to us as the passive house consultant, or, you know, whatever consultant, because, you know, we need it to mitigate the thermal bridge caused by the top plate here. You know, without this exterior insulation shown, you know, it can get tricky in terms of how this is all going to actually perform. And that was the point of that detail. Attic hatches. Attic hatches, the long and the short of it, you end up with a lot of insulation on top of your attic hatch. In a, you know, if it's an R60 ceiling insulation, you know, that can be a lot of insulation. And so wanting to detail this in a way that it's not only constructible, but that you can also actually, like, you know, use the attic hatch. There's a lot of products on the market that, you know, you can buy that will achieve this. Not necessarily to R80 or R60 as indicated here. So some thought needs to be sort of, like, you know, put into how it's going to get done, how we would do it. Some more details. We're coming to the end of sort of like the detail heavy portion of the presentation, but rim and band joists, I think I alluded to it earlier. It's a great spot, in my opinion, in our opinion, to do spray foam insulation. There's a lot of framing that happens in this rim joist area. You know, this is a floor above, this is living space below. To stuff a piece of fiberglass insulation in here is not going to perform all that well. It's going to be very hard to get it to a grade 1 or grade 2 install that we would be looking for on an Energy Star or passive house project. So having spray foam insulation, which is what is shown here, you know, sort of fully fill the cavity is a great way to go. It's going to help air seal these connections between this piece of framing, the top plate of the floor below is going to benefit from that a little bit. But in terms of it not being a silver bullet, you know, you still need to make these air seals between these two top plates of the floor below, because you know, the spray foam insulation is not going to be spray applied here. You still need to do your traditional air sealing here. Same thing with the floor above. The only thing that, well, no, I take that back. You know, even this connection from the bottom plate to the subfloor, you know, is not being addressed necessarily by the spray foam. It is on the underside, but it is not being addressed on the top side of the framed floor above. So this is shown here as a great option for the thermal control layer, not necessarily the air control layer. The wood framed, getting the details right, talking about mock-ups here, sort of shifting gears into how to do this consistently across a large project, and, you know, doing it the right way the first time. Mock-ups are a great way to do it, and complex mock-ups are even better. So this mock-up is, you know, the project team here sort of went all out. They picked a wood framed wall, or sorry, any framed wall that has, you know, complexity to it. It's got inside corners, outside corners, it's got a window. You know, the idea of doing a mock-up, like, don't just pick a flat wall section with no penetrations and no windows and no corners. Like, that's not going to really help you visualize the different details that are kind of come up during the build. You want to pick something that has some complexity to it, so everybody, all the trades, can get on the same page with how it's going to be addressed in the field. There's going to be some back and forth with the design team here, you know, how everything is going to get addressed. Here's some more wood frame mock-ups. Again, critical junctures, inside corners, the window install, put a roof on it, put a foundation on it. Those connections are super important. You know, if you have all of these connections sort of accounted for and you can practice doing them, it's going to really, really help and really result in a better performing building in the real world, not just on plan or in a model. So we've got another poll here. I've got about 7 more slides to go through, and asking you all, why do you think continuous insulation is so hard to achieve? Wondering if you have any thoughts about this. Like I said, we're getting close close to the end of our slides. Yep, agreed. The corners, the angles are tricky to do. Sequencing, absolutely. Who's doing what, when, and how? Yeah, penetrations a bit. All right, I'm going to move on. Our next image is going to be talking a little bit more about spray foam. We had said that it wasn't not a silver bullet, and here's some of the reasons why we see it not being a silver bullet in a lot of projects that we're looking at. Our preference and what we advise teams is to use spray foam as your insulation layer when you're trying to get to high performance, you know, to that passive house level. Don't rely on spray foam as your air barrier exclusively for these higher performing programs, these higher performing projects, because there can be a lot of challenging areas to address. You can see the installer here, you know, working through This is the underside of a garage, parking garage below. This spray foam is going to do a great job as a thermal protection for between the two spaces. But really the air barrier is probably the concrete deck that's above this. That's where the air barrier is. And some of the reasons that we're talking about this it's from experience, right? Like, it's very deceiving when you see spray foam that looks extremely well done. But in reality, there's gaps that, you just can't see. So the example here is, this spray foam, the field of the ceiling here was installed, originally. It came in, we're like, wow, that looks great, good job. And then when it came time to blower door test the building, it was having some issues, it was failing. So again, this is up in the attic, hard to get to. So you can see that this spray foam was done after blower door testing sort of showed us that there were problems. This is the IR image of it. You can see that even with the remediation, it looks like that spray foam is going to stop any air leakage, but it didn't expand up into the gap that's sort of like rising up into the top of the image. And so when you look on under infrared with the blower door running, under depressurization, you can see, there's air leakage coming out the side of it. This cap here, right, wasn't hit. And so it's sort of like, plugging a dike with your finger as the water is coming in. It plug one hole and it sort of pops out the other. So it's just very deceiving to be able to inspect and say that, the spray foam is acting as the air barrier without doing any performance testing along with it to sort of corroborate that.
Scott, there's a question, and you may be getting to this in your final slides, but just around, obviously spray foam addresses some of these challenges from an air sealing perspective. But when you start to consider the embodied carbon, how do you respond to that, or what solution do you see for projects that are trying to be embodied carbon conscious?
Yeah, it's challenging for sure. And so we've come to try to say, with spray foam, trying to use it in limited instances where there's no other way to sort of solve the problem. But it's not necessarily the best solution from a number of perspectives, not to mention, the global warming potential that the question arises, which, it's gotten better over the years, but it's certainly not carbon neutral. It's not carbon positive, like, using cellulose insulation, you could look at that as a way to sequester carbon within your enclosure, right? Like the carbon from that pulp, from that tree, sort of being sequestered in your cavity. So for large areas of the building enclosure, there's other options to address, to use, that would include a very good air barrier coupled with, a more traditional version of insulation, like a fibrous insulation or something like that. It's going to perform just as well, probably going to cost a lot less to construct, and it's going to, in our experience for these large areas, it performs. It's just hard to see those areas where it's not installed 100%. And so we've had some issues over the years with those projects sort of relying on the spray foam to really give a great air seal, and we come up short sometimes. Yeah, and I think that's kind of we're getting to the end here. So these last couple of images here just showing about spray foam coverages. Rule of thumb for verifying this is to take a couple of different measurements of the spray foam thickness and the wall that you're looking at, average them together to arrive at what your sort of like overall average R value is, and using that to make a determination as to whether it's good or not, whether it's meeting the R value requirement, right? But yeah, that's it. Are there any other final thoughts or takeaways from the presentation today? If you'd like to share them, we've got a poll here to be able to do it, but can also just sort of talk about it. I don't really have any other slides. So
that's great, Scott. Thanks. Yeah. Well,
yeah.
It looks like we're pretty well caught up with the questions for right now. A few folks have asked where the recording of today's webinar will be. So that will be emailed to all attendees. A link will be emailed as part of the post-webinar survey that you'll receive, and it'll also be posted to the Connecticut Passive House website as well. And also just a plug that we have part 2 of this training coming up next week as well. So if you're not signed up for that, certainly be on the lookout for that.
Yeah. Yep. So I'm looking forward to joining you guys again. Thanks for listening. We will talk more about sort of the air sealing piece of this puzzle on the next one.
Yeah, looking forward to that, Scott. Thanks again, and thanks to our sponsors from Energize Connecticut again for putting this training on for everyone. And yeah, we look forward to the next installment.
All right. Thanks, everybody.
Thanks.
Thanks, Scott. Bye.
Bye-bye.